listed there. All right, so let's look at the first supplementary law. There are many ways. This proof is very simple, but I'm going to put this into a field extension situation so that you get used to it, so you see the full proof and get more familiar with that context of a full proof. Okay? So let's start with this one and put it into field extension context. Let me organize myself a little bit. So here's a little kind of discussion that leads to the idea. So let's think about the situation that -1 over p, Legendre symbol, is -1. What does that mean? It means -1 is not a quadratic residue, right? So when we have this non-square, we consider the field extension, right? Anybody remember what kind of field extension we considered there? -1, not square, not a square. Then we considered fp are joined by square roots of that non-square, right? -1 is not a square, so we adjoin a square root. That gives you an actually larger field, right? We have all the usual finite field of p elements. -1 is not a square, so if you put a square root, it's not something that exists in fp, so it's an imaginary number, right? You can call this an I, it's an actually imaginary number. How about f5? f5 is not the case, right? -1 here is a 4. 4 is a square. So -1 in that case, you don't really have the bigger field. Correct? So that's the situation. But so what is this number? This number is actually, it has nice order. What is in general, if you pick a number that is not like this 1 or -1, you can't say that what the order is, but this one has nice order. This one, if you raise it to square, that becomes 1, right? No, that one. That's order 2. This one is, let's think about it. So I'm going to call zeta. Join that. All these elements, and we are joining to the finite field or inside element of the finite field, they all have an order, right? And calculating order is in general is not possible, but this very special element -1 and mod p, no matter what the p is, you can calculate the order. So first you square it, you get a -1, right? And still not 1. P is an odd prime, so if you raise the next power, then you get 1, right? So if you just have this equation, it doesn't mean that zeta has order 4, but we have this equation, right? So from there we know order must divide 4, correct? Order must divide 4, but order is not 2, because square is -1, right? Therefore, together it says that order of zeta is 4. Right? All right? So we were able to, no matter what p is, which is for other numbers, you will never have this solution. No matter what p is, the square root of -1, imaginary number, for the finite field has what order? Order of 4. Is that correct? Okay? So the element we're looking at in this field extension is that whether there's going to be an order 4 element or not. Right? So here's a statement. If fp has an element of order 4, if and only if, let me change to if and only if statement, there's no if, fp has an element of order 4, if and only if this adjoining the negative root, square root of -1 is actually the same as fp, this, the square. That element we're looking at is order 4, element of order 4, it was already inside this fp. So that implies that this one exists, this element, zeta, is inside of fp. So in the first place, the square root of -1 was a square because that element exists inside the ball. So let's see. A little bit. So let's think about. Well, this part's easy, right? If square root of -1 is inside FP, you adjoin that element you thought about, you joined it, it turns out it was already inside FP. That's what this means, right? If it is so, we have an element in an FP, so therefore we have an element of order 4. That's kind of easier statement, right? Well, let's prove this part. If FP has an element of order 4, then square root of -1 is inside FP. This is what we want to prove, right? Some element that we're looking at. Is that right? So if you add that zeta value, or square root of -1, to FP, you don't get anything new that was already inside that element. Okay? So, so here's a proof. Sorry that was written in a tiny room. So let G be such that its order of G is 4, and of course G is coming from our finite field FP, right? Is that all right? So this root 2, and then that's one statement. And another statement is a root -2 has order. What's the order of that element? Root of -1, which we call zeta. So let me stick to the zeta. Zeta is at the order. Remember this part? What was the order of a root -1? Discussed it up there. Was 4, right? If you raise to the 4, so order 4. So I'm going to write down the order 4. All we want to conclude is that the zeta can be written in terms of G. That's what we have to show, right? So in this space, I'm going to call field F to be finite field with that zeta. Whether zeta is in FP or not, I'm just going to call that field F, potentially bigger than our smaller field FP. Maybe it's the same thing. But it's a field. It's a field. And that's a key statement, which we haven't proved yet. It was just part of that theorem and part of the reading course. It says it's a field. So I'm collecting it here. This is counting lemma. I'm collecting all the x's in this potentially bigger field, especially non-zero element, such that x to the 4 is 1. Okay? Then it has at most how many elements? 4 elements. Remember that counting lemma? Right? Yeah. If it is a field, there cannot be more than 4 elements. So how many elements do we have here? Let's think about G. G, we have an element of order 4 in there, right? In FP. So let's play with the G. G is a G bracket. How many elements are there? This is not the collection of order 4 elements, right? Elements, this is a collection of elements that divides 4. That's what this is, right? Think about order 2. If it is squared, it's already 1. 4th power is still 1. So this is a collection of all the elements of order dividing 4. So G is an element that was assumed that it's order 4 there. So it's a G to the 0, G to the 1, to the 2nd, to the 3, and to the 4th going back, right? Is that right? So this is already 4 elements. Why is there no repeat? If there's a repeat, the order of G will be smaller. Order of G means this really has 4 elements, right? But zeta must be in there too. So let's write it down. Continue. It's this tiny space here. I'm going to write it. On the other hand, zeta is in that. So what is the conclusion from the, sorry they're going back and forth like this. I showed that G has these 4 elements in there, right? Together with this counting lemma, what is the conclusion? That bracket G is equal to that set here, right? G has order 4, therefore is in there. Everything is in there, right? Every element in order has order dividing 4, and this one has at most 4 elements, and we have full 4 elements. Therefore, the key thing is that this is a collection of elements from where? Potentially bigger field, not the bottom field, a potentially bigger field, right? If you collect not only from FP, from a potentially bigger field, you don't get anything new. You still have at max 4 elements. That's the field. That's strong property of the field that we haven't even proved. Even if you throw in, it still remains a field. The fact that it remains a field still makes this one at most 4 elements. We already have 4 elements there. You don't pick up anything new. Did you have a question? Yes. That is the counting lemma. That's what the counting lemma does. This part's easy. This part's easy, right? And you're questioning what is the other one is there, right? The counting lemma says it has at most 4 elements. Counting lemma says it has 4 elements, right? What's in the bracket? It's 4 elements. Subset has 4 elements. That's realize the maximum possibility.
And there's only one subgroup that has 4 elements. So that makes sense.
Right. We're talking about the superset has at most 4 elements, right? But you found a subset that has 4 elements.
What is a superset?
Because you said you easily understood that bracket G is inside there, right? Because its element came from there. So subset has 4 elements, and the above counting lemma said it can only have 4 elements at most. So it must be the same. If it is a smaller set, it must have a fewer elements, right? So if you go back, what difference does it make? Where is this difference kicks in? Is this one here, field? This statement made the difference. Without it, you can't conclude anything like that. It's at most 4 elements. Where that come from? It came from the fact that we're still in a field. This defining equation right here, right? Defining equation next to 4 equals 1 will not give you any more example if you look at bigger and bigger field. That's one way to summarize it. If you happen to have this universal defining equation, if you look at a bigger and bigger number system, it doesn't give you more and more elements. It always gives you at most how many elements? 4 elements, no matter how big your field is. There's no more than 4 elements. Why is that? Because the number of solutions for polynomial degree 4 is at most 4 over a field. As simple as that, right? But if you don't really seriously think about this, what property of the field really makes a difference, it's puzzling. And if you especially think about chain of reasoning, if you seriously think about it. All right? Make sense? So we already have everything in there, and you have to, on the other hand, zeta is in here. Don't you think? Why is that? Zeta came from that potentially bigger field, and whose order is 4, therefore is inside there, right? Right? Yeah. So everything in here is in power of G. Therefore, what's the conclusion? Zeta is G to the K. Isn't that right? What do you think? Is the argument correct? The last bit. On the other hand, zeta, is, if you raise to 4th power, is 1. Therefore, it's in the same set. Everything here in that set is now, I'm changing the subset to the equal symbol here, equal. Using the counting lemma, I show that these are equal, exactly equal, right? So anything in here must be power of G. Good? So what does that mean? Zeta is in where? FP. G generates everything. Zeta was the power of G, therefore it's inside this FP. Right? So let's go back in here. FP has an element of order 4. The zeta, we were just imagining it, right? Square of it become -1. It happened to be in FP. right? That imaginary number that we're thinking about is actually an FP. I pretended this imaginary number, but if you have this element, have an element of order 4, and if you really look at primitive roots and all that, then you can kind of have a different interpretation of this. But in the more complicated setting, it's important you understand zeta and something we grab it from FP, potentially different, right? And you have to make this clear identification, like I did with it using the counting lemma. So all that goes to is a strong property of the field and defining equation. You don't pick up anything new, the same old thing. Good?